Hi, everybody. My name is Diskin, and I'm the CTO and co-founder of Awesome, a startup company that specializes in identity and access security. I've been a cybersecurity researcher for many years. I worked for Intel and Palo Alto Networks and many other places. And today I'm going to talk about the recent research we did about extracting clear text passwords and impersonating multiple users in Okta specifically. Which is one of the largest identity providers there are. Let's get started. So what am I going to talk about today? First off, I'm going to talk about the background, Passbleed, the set of security weaknesses that we found in Okta, IdP, the Orange Book, and some background about the trusted computing base for those of you that remember this type of stuff. If not, it's worth searching. I'm going to talk about graphs and knowledge graphs in security and how we use them as part of our research methodology to methodically find logical vulnerabilities of certain types, obviously. And I'm going to discuss the research process that led to discovery of the Passbleed issues, which include two main issues. One is the ability to bleed clear text passwords via SCIM protocol. And the second one is to impersonate anyone in the main company hub through members of the spokes of that hub. So lower security domains getting to impersonate higher security domains. And lastly, I'm going to provide a summary that will include how to write your own logic vulnerability detection suits very easily. Discuss a little bit about the public reaction to this set of security weaknesses and what we've found, and finally talk about what we've learned and where to go from here. So without further ado, let's get started. So as I mentioned, we found several security risks in Okta. Those were not recognized as vulnerabilities. Okta believes that this is part of the valid function of their platform, and they are the CNA, so they get to decide. It's important to note that while not vulnerabilities, these issues allow less privileged attackers in Okta to gain access to the super admin privileges or extract all the clear text passwords, which might be intentional. And in this talk, I'll walk you through the research process we went through. And I will touch on a systematic approach to discovering these certain classes of logic bugs, such as broken access control. So way back when hacking and security was just starting, and honestly, I was 2 years old, there was a great book called the Orange Book, colloquially, or the Trusted Computer System Evaluation Criteria by the US Department of Defense. And this evaluation criteria was about defining what is secure and how to secure computer systems. It was one of the must-read books for any hacker or aspiring hacker at the time. And it defined a concept called the Trusted Computing Base, or TCB in short. And TCB means all the system elements that are excluded from it should not be needed to be trusted to maintain the protection. This is the best definition for the Trusted Computing Base. And this basically means that the TCB are the things you have to trust for your platform to work securely. So I'll get back to the TCB in a moment. I want to talk a little bit about graph networks in security. So what are knowledge graphs, or known as KGs shortly? Knowledge graphs are basically networks where you have nodes representing certain entities and edges representing certain relationships between those entities. And where the knowledge graph allows generally any type of relationship with between any type of entities. And there are a lot of applications of knowledge graphs or graph networks in general to cybersecurity, usually with very limited set of relations. So, for example, Maltigo is a very classical tool that uses social and even is used for social and even attack surface mapping. Attacker thinks in graphs. Bloodhound, which is very famous AD-related tool, an entire category of products called Cloud Infrastructure Entitlement Management, which protects cloud service provider identity systems, and various attack simulation tools, and the list can go on and on and on, but we're not here to talk about that today. So what do I want to talk about? How we use graphs to map trust and discover vulnerabilities. So knowledge graphs can basically use to systematically find these logic vulnerabilities. And how we do this is by defining nodes as assets, privileges, or actors. It's important to include the actors and the privileges where it's applicable. Edges as the trust relations between these entities, defining who can do what or who is allowed to do what and who trusts which element of the system trusts which other element of the system or not of the system to perform an action or achieve a certain level of trust. And what we innovated in a sense is that we add mistrust edges, which represent lack of trust or who shouldn't get what in a certain sense. What this creates is basically that anywhere that you can find a chain of trust that ends with a mistrust edge, you found a vulnerability. And while we're doing this, one, it enables collaboration in teams, where different team members can research different elements and don't have to know every finding of the other team member. Second, knowledge preservation. By putting this data on a graph, if we come back to this application a year or several months later and we don't remember anything, all the knowledge is preserved. Three, visualization for manual work and prioritization. Visualization allows us to do manual work and guess places where we might want to invest effort in research and prioritize. And lastly, automation. Sometimes the vulnerabilities and the chains of connections to find the logic vulnerability are very complex. You can't necessarily hold them in your head. By translating that to a graph and analyzing the graph through graph analysis algorithms, even very simple ones like cycle finding, we can literally reduce our pains. So without further ado, let's go to an example. Let's say I have super admin privileges in Okta, which is my example for today. And I'm defining the first trust relationship. Being usable by someone is a type of a trust relationship. I'm saying super admin privileges are usable by super admins. That makes sense. Now I'm saying super admins are identified by a successful login, which depends on, which is another, and identified by is a type of trust relationship. Depends on is another type of trust relationship, right? Successful login depends on password verification and or MFA as well. And at this point, I think we're sort of agreed on the basic principle. Now, before I continue, I want to give you a short explanation about the connection between access relationship and trust relationship. In general, access relationship, for example, if I can access something, it means that something needs to trust me or the component in the system that is accessing it by definition, unless there is a certain filter or control around that. And this is how we graph that. At this point, let's start talking about the security weaknesses that we found in Okta. So first one is about the ability to bleed out clear text passwords via the SCIM protocol. So let's start with the first question. For those of you that don't know, what is a SCIM? SCIM is an identity provisioning protocol that is used to automate the synchronization of user and group data from centralized sources like IdPs, SSO providers, directories, to downstream applications. And interestingly enough, this diagram comes from the Microsoft documentation. Okta have extended SCIM to support password synchronization. And they are doing that by sending passwords in clear text. Now, going back to the story that we just started earlier, or the graph of privileges, let's go ahead with this analysis as we've been researching it. So we started by mapping the application, which is a standard action that we do every time we start with an application. At which point we sort of realized that in order for there to be synchronization of passwords, there has to be a decryptable password store. So we added it to our map. We added to the map the trust to the SCIM password sync feature itself, which trusts the SCIM server operators, who get these passwords in clear text and are assumed to protect them securely. Now, these might be actually valid enterprise applications, at which point we sort of are okay with that, although we're trusting that the enterprise application vendor, third-party company, employees with the relevant access to see, for example, the network logs or firewall logs or read the submitted passwords are not making any use of it. And the other thing we're trusting is that other SCIM server owners are not the target of this provisioning, and which could actually also be the targets. Now, who's choosing this? The admins are these either SCIM server operators or valid enterprise application targets that are acting as SCIM servers are chosen by the admins in Okta. But admins are clearly not allowed super admin privileges because they are a different level of privilege, which is much lower. So we got to this map, and obviously I'm showing you only the interesting parts. The map is huge and it's covering a lot of other elements of the Okta application, which we didn't yet. I didn't include in this diagram because that would be really confusing. But we actually, as promised, found a cycle that goes through one mistrust edge and a set of trust edges. And now, basically, when we find this type of cycle, we backtrace when we find it in research. So I'm going to start from the admins, and I'm saying, instead of chosen by, I'm saying can choose other SCIM server owners who will be the SCIM server operators, who will get the SCIM password sync data from the decryptable password store, which will include the clear text passwords, which allows successful login as super admin, because identified by is reversed to as, which is makes them be able to use super admin privileges. So actually, by backtracing, I now know the set of actions that I need to do to try and exploit this logical vulnerability. Now, as I go on, as we found this, I started with telling Chen, who was on my team, look, we made a mistake somewhere. There is no way that an admin can access all passwords, including super admin passwords. I'm sure we're missing something, so let's test again. And we tested again, and we got the clear text password of a super admin again. At which point we were pretty sure that we actually found something. So Chen came up with the idea that probably the admins are either very highly privileged or rare or whatever. So we started by checking the frequency at our customer environments, because we are connected to their applications, especially identity systems, to monitor those. And we found that some of our customers, especially the larger ones, have tens or hundreds, or in some very rare cases, of admins. At which point we said, let's try and understand why do they have this. And it took us several days to analyze this, but we got to a conclusion. And the conclusion was, this is de facto the lowest built-in role that can assign users the permission to use apps in Okta, which is why when you want to democratize access, or basically assign anyone that is not one of the core admins in IT of the Okta platform itself to give users access, most organizations make these people app admins. So let me dive into a small bit of technicality. This is the actual JSON payload that you see on the right-hand side that is sent by Okta to any SCIM server. I actually, rather than take an example that I generated myself, took an example from the Okta documentation. And I like to stay of humor with the password that says very secure. And this is the actual password. This is not obfuscated. It's sent in clear text. And the other piece that is interesting here is that the other data that is transferred is in part PII. And it's transferred also in clear text if you're sending it over HTTP, which there are no actual controls to prevent. So let me describe a few attack scenarios based on this. So attack scenario 1. Let's say you have an insider who is an app admin. He is bribed, let's say, by some initial access broker, which is a very common activity pattern, as we've seen recently with, for example, the Lapsus group, who like to use it, but many other parts of the cybercrime ecosystem are also using it. He's exfiltrating those passwords to a server that he controls, and basically at this point he's making money, and goes back to the valid configuration. Let's talk about a different scenario. Let's say the attacker compromises one of the tens of app admins that an organization has. They exfiltrate the super admin password or an automated account password, log in using that password, and they may need to beat MFA, at which point the privilege escalation is successful and they're done. Lastly, let's talk about the situation where a naive app admin configures SCIM to point to some HTTP and not HTTPS, unencrypted target. The attacker can sniff network traffic at this point, anyone that is sitting in the middle or able to sniff traffic in the middle. And they will find passwords and PII, which they then can monetize however they want. The second security issue that we found is about the ability of anyone in a spoke, which is a subunit of the organization, to impersonate anyone in the hub or the main unit. And to explain this, let's start from talking about how the Okta hub and spoke architecture works. So the hub and spoke architecture is basically an architecture that allows dividing multiple tenants of Okta to, for example, business units, acquired companies, outsourced companies, to work with a parent company or a main company who acts as the hub or the central unit, while all of those subunits are acting as spokes. Now, the diagram on the screen shows one of the recommended deployment models by Okta, a large organization with multiple business units where the business units are the spokes. They are talking to the hub, and the hub is talking to anything else that you need to access. So it could be on-premise resources, it could be cloud applications, and so on and so forth. And every business unit gets a spoke, and all the spokes are connected as identity providers to the main company, which is acting as the hub. Now, I'll get back to this, but to give you a hint, identity providers are trusted by whoever they provide identities to, by definition. Second example of a deployment model is a third party, including contractor and outsourcing. And again, this is taken from the recommended Okta documentation, connecting to a retail company hub. And each third party provider gets a spoke. All spokes are connected, again, as IdPs to the main company and disconnected appropriately. And there are more deployment scenarios like M&A, geo-location-based, and so on. Now, back to our favorite diagram. Let's continue it in a different direction from the one we looked at before. So a successful login trusts any IdP who provided the credentials and verified the login. And this IdP could be any spoke. There are also other types of IdPs. I won't get into this now. And any spoke depends on the user store in the default configuration to know what actual user data to send to the hub. And this user store in Okta is controlled by any org admin or super admin roles. In addition, anyone that can actually edit the configuration of the username stored sent by the org to org application, which is basically the application who is implementing this hub and spoke architecture from the side of the spoke, can choose which username anyone gets. So that means they can also control the username sent to the hub and therefore identify as anyone they want. So, and this is, by the way, inherent to any identity provider. This is not unique to Okta. This is the way modern SSO and identity providers work. So, now that we know that these could spoke app or super admins or org admins in different cases could actually control the identity that gets sent. Who are these folks, organization admins or app admins or super admins? They could be the org unit spoke admins or the M&A acquired company spoke admins, and they could be even external company employees in the example of the outsource company that is working with your company and connecting the actors via the hub and spoke configuration. Now, that actually means that they should not be allowed to have this access, right? Because they are not the super admins at the main company or the hub company. Now, going backwards, what would happen, same as before, to analyze the attack path itself? The org unit spoke admin, or the external company employee who has this access, might be a super admin or an org admin or an app admin in his own Okta tenant, the spoke. In the spoke, they will make sure that the right user is either created or configured into org-to-org application as the identity of the super admin, which allows them to identify and log in as that user, which allows them basically to become to use the user of any existing hub super admin, which makes them super admins. Grants them super admin privileges in the hub. Now, when we got there, Chen came up and he said to me, look, Gal, there is no way the hub trusted to the spoke implicitly. And I said, but this is what it means to be an IdP, right? An identity provider provides the identities. And it says so in the white paper on the Okta site, the white paper which you saw the screenshots from earlier. And Chen was asking, like, you're saying that the admins of subunits, the acquired companies, outsourced companies, have hub admin access, and there is no way. They must block the duplicate usernames there. And then I searched further and I found the documentation. And it literally says, out-of-the-box duplicate name support is a feature. And besides, we actually managed to create this flow, and you can see the video on YouTube if you're really interested. And, you know, at that point, Chen was silent. And I have to tell you, it's fairly rare that Chen is silent. So we came up with the question of why is it like this, right? Because it's not random. It's not it's obviously by design in a certain sense. It took us several days, but we came to the conclusion that it's the easiest way for Okta to implement a functionality that is similar to Active Directory OUs or trees and forests. And basically, this is what Okta went ahead and did. And Okta added controls to prevent administrator login from IdP spoke to hub. But it's a regular expression, which is nearly unmaintainable, right? Unless you're very, very sure that you can match all the admins now and in the future into this regular expression, you're very likely to fail to implement this. The other thing, and by the way, it's not on by default. You need to actually figure this out. And the other thing is, even if you do that, it doesn't prevent downstream app impersonation to other users, which could be admins in some of the applications connected to the hub tenant. And there are some ways to prevent downstream impersonation. Specifically, there is one way that we've found, which is to configure your Okta in a way that actually forces the usernames from every IdP to have a certain prefix or suffix that can't be changed. Now, the interesting thing about this is that this capability is not documented as a security feature, and it requires the customer to perform an architecture change in all his usernames and downstream from the app further. So again, not actually news. We haven't found this in any of our customers, but this is what it is. Now, let's talk about a few attack scenarios based on the hub and spoke architecture in order to escalate privileges. So one is, let's say there is somebody in a small company that was acquired and added as a spoke, and she's compromised. You know, the big company that acquired it could be a Fortune 500 company. The small acquired company could be a 5 or 10-man company with very low security standards. At which point the spoke admin is used to impersonate super admin in the hub, and success for the attackers. Second scenario that we can talk about is a third-party outsource company is connected as a spoke, and the admin in the spoke, which is not an employee in the company, impersonates the CEO of the company that hired his company in different applications. He could gain access to confidential data. He can even manage to transfer money, and later ransom-demand arrives. Ubiquity is a good example of what happens when people want to do things like that. Insider admin creates an Okta developer tenant. This is another example. He connects or modifies a spoke to point to his spoke, which creates basically a path that he controls the access in. And he continues to maintain his access post his retirement or departure from the company. And then God knows what he does with that. So I hope that was interesting up to here. Let's really talk quickly about the conclusions, some reactions that we've gotten, and a summary of this research. So first off, I want to tell you, build your own graph analysis. It's very easy. As you can see here, I have an example based on the NetworkX library, known as NX shortly. Basically, you can do it in a few lines of Python to add nodes, edges, and basically allow the access that you need. Two, you can then use the same methodology that I've mentioned to find cycles for a specific target or for any target, as you see in the two different lines at the top. Sometimes when your graph is very big, you want to focus on specific targets because it becomes costly. And lastly, you can visualize very quickly using NetworkX. You will learn as you start using it that there are better ways. Obviously, you also want to have a good backend for this, probably not the files that NetworkX is exporting to, but things like graph databases like Neo4j or ArangoDB or TigerGraph and so on. Really don't forget to save your graphs, otherwise all your work will be gone. But again, the real value here is the ability to collaborate and maintain and preserve the knowledge and automatically analyze it. So I want to have to say a few minutes, like 1 minute to talk about the public reaction we got to this research. So there was lots of buzz regarding this. I have a few questions that I recommend everyone to ask. If app admins can get the super admin password, why bother having a different role at all? Now, I got some people saying they still have MFA in certain cases. This is true, but if one factor was enough, why did we configure MFA or add second factor or multi-factor authentication in the first place? And if the master password should be shared, why is no one else in the same field doing this? neither common password managers or SSO vendors supporting password-based SSO, none of those that we've found support sharing the master password. Now, if spokes represent a lower security domain, in the case of hub and spoke architecture, which could be OUs, third parties, or M&A, what is the default configuration allowing them to impersonate anyone in the higher domain, the hub? And this is advertised clearly as a feature. And lastly, I want to say that there are certain losers that try to capitalize on opportunities to discredit others, and whoever I'm talking about knows what I'm talking about them, and they are not going to get any reaction other than this. So to finalize this, I want to say that we have worked very closely with the Okta security team, and we really appreciate their focus on this. And I think that on one hand, those are not considered vulnerabilities, but they're part of the system specification in Okta's eyes. But on the other hand, I really appreciate their intent to improve their platform. And I know that they have plans to add controls around these areas and improve the separation between roles. And I will end by saying that we have more disclosures coming soon, not just for Okta, also for other vendors. And finally, just to summarize everything I went through, one, knowledge graphs are a very useful tool to collect knowledge for attack and defense. And you can apply them to do trust analysis at scale and systematically find logic bugs. And this is very cool, I think. I think it's also very useful that you can preserve the knowledge in this way, automate the processes, and collaborate in large teams without everybody needing to know what others are doing. And I think there are certain implications to pass lead issues. One, app admins can get anyone's, including the super admin passwords, meaning we are likely to see certain password dumps coming soon, clear text passwords, so be aware. Or if you see one that is unexplained, this is worth investigating. Spokes in hub and spoke architecture, admins can impersonate anyone in the hub or the downstream applications in the default configuration. So understand that whenever you connect to spoke, you're putting your entire organization at risk, and plan accordingly, apply the security controls, see what I discussed about the naming prefixes and so on. And lastly, don't believe the FUD. Our industry is full of FUD. It's very, very sad. I hope you enjoyed this talk. And if you're interested in learning any more, I'm happy to answer any questions now. And you can find me on Twitter. I'm happy to answer questions there as well. You can see our YouTube videos and read our blogs around this. Thank you.